Good day, ladies and gentlemen. The talk of my presentation is high energy collisions of particles in the vicinity of black strings. Yeah, the content is simple. We will introduce the black string spacetime and aim of our research, and then we will consider some process of the collisions of two particles for three cases. For the static black strings, the black string emerges in external magnetic field, and the rotating black string, and some concluding remarks. So black strings are some objects which came us as a correction to the well-known Einstein gravity through the string theory. And as we know, the black holes are the solution to the for the Einstein equations, but the black strings is some extension object with additional dimension. It came as some phenomenological solution. So, as I said, it came from the string theory, and it gives us an infinite series of the symmetries, and this range of symmetries can be separated by the range of horizon topology. And for example, the black hole's topology has a S2 four-dimensional black hole, because the cross-section of the horizon is a two-sphere, while if the black hole is five-dimensional, it would be S3. But in our case, since it's extended to one dimension, which in principle can be compactified at infinity, and it has that horizon topology S2R1. So recently it has been pointed out by Banyada, Silk, and West that two particles colliding near the extremely rotating black string can produce the particles with very large energy. In principle, this energy can be unlimited. And but the problem is that, as it was pointed out also by Professor Stuprik, that these collisions occur for the very fine-tuning values of the angular momenta. And our question is, does it always work? Which means, can this process be transported from S2 topology, which originally investigated for the Kerr spacetime, to the solutions for the black string spacetimes? So the static black string or non-rotating black string spacetime metric has this form, and it has a difference from the Schwarzschild metric by only the additional dimension d omega. And we can, due to the symmetries of the spacetime metric, we can introduce the conserved quantities. And in our case, in five-dimensional spacetime, we have three conserved quantities: the energy, angular momenta, and new constant of motion, which is related to the additional dimension, which we included. And before starting the collision process, we have to clarify the motion of one particle and the possibility to get the horizon of the black string, and we can use effective potential, and if its energy level for the flat spacetime are shown by horizontal dashed lines, and we see that increasing of the new parameter also increases value. And for the particle to reach infinity, its energy should be higher than its initial energy in the flat spacetime. And the final state of the particles entirely depends on its momenta. And we see from the left plot that if the angular moment is too small, the particle simply fall onto the horizon, and we will never see we will see it later. We will never see the high energy. While for the right-hand side plot, if its angular moment is too high, it will not get the horizon. So here is some examples of trajectories by the numerical simulation, and it seems that there is some critical angular momentum for which the particle can directly fall onto the horizon and collide with another particle. And the center of mass energy of two such collisions we can calculate by this simple formula. And here is a schematic picture: two particles colliding in the vicinity of the black string, and the energy has this not very good form, but we have these two terms, and if the particles colliding in the region are equal to, or very close to the horizon, it seems that it should go to infinity, but it is not so, of course. And if we will take limit, this energy is finite, and moreover, this energy is very small. But as we see also, it depends on our new parameter on J, in contrast with the of the black hole space-time. And we see that if we will increase this new parameter, let us call it string parameter, and if we will increase this string parameter, the center of mass energy will also increase. But it is not so very good, because this energy, not because of the collision, but the initial energies of two particles also should be high. That's why it is not enough for us, and we will introduce a magnetic field in the black string space-time. Okay, so it is very important because of several processes, and it is astrophysically relevant to consider the magnetic fields. And the question is how strong or how weak our magnetic field in our approximation. So we use a test field. So magnetic field is test field in such sense that it will not change the gravitational background. So we can compare the gravitational effect of the electromagnetic field, just taking the energy of the, comparing the energy of the electromagnetic field with the energy of the gravitating object, and we will take some maximal value of the magnetic field, and we say that our magnetic field is very, very small in comparison with these values, because, as I said, it's just a test field. And again, we can find the due to the symmetries of the space-time, we choose conserved quantities. It is the energy, angular momentum, again the new string parameter. And what is the difference? We have some new parameter which is related to the magnetic field, but it goes show us the interaction between charge and external magnetic field. So it's simply a Lorentz force, nothing more. And it is very important when we consider the motion of the particle in the external magnetic field to consider the circular motion of the particles, of charged particles, of course. And we can find the positions of innermost stable circular orbits, and just taking the first and second derivative equalized to 0. And we see that when we increase the magnetic field, our ISCO will ISCO radius become closer to the horizon. And since we know the equations of motion and other things, we can find the velocity and gamma factor. And we see that in the ISCO region, as it is expected, the velocity is almost constant, but this velocity depends on the string parameter, and we see that the increasing of the string parameter will increase the velocity of particle from 0.5 of the speed of light till, in asymptotic of course, and till the speed of light in principle it can increase. So let us directly go to the collisions of two particles. We will consider it different cases. First is the simplest one. It is a head-on collision of two particles when we take two particles with the same mass and the same circular orbit and the opposite charge and opposite momenta. And we will calculate the center of mass energy, and we see again this energy is not very large. But of course it again depends on J, and this J can be arbitrarily large, but it is not because of the collision, not we was expected. And we will go further and consider another type of the collision when one of these particles is charged and revolved at circular motion, and second particle is neutral and fall from the infinity where it was at rest at infinity and collide near the horizon of the black string. And for this maximal, so the center of mass energy has this form, but the maximal energy is this one, and we see it. We see that it is fourth root of the magnetic field, and this field again, we can take very large field and it will grow up. But there is some limitation, astrophysical limitation for the magnetic field, and it is 10 in power 8 Gauss for the mass 10 solar masses, and 10 in power 4 Gauss for 10 in power 9 masses. So in principle, we cannot increase it as much as we want. So that's why let us go further and consider the rotating black string as a particle accelerator. So the space-time metric has this simple form. It looks like to the Kerr metric, but with additional dimension. And horizon, as always, as usual, it's located here. And again, we find the conserved quantities, but here we also, in this space-time, we have the maximal possible value of the angular momenta. So, because we have to, we take this condition from the conditions that we consider consider the particles outside the horizon. So we take the dt over d tau more than 0 positive, and it is very important to find again the limitations for the angular momenta, and to achieve the horizon for the rotating black string. And these limitations give us such values for the angular momenta, and this angular momenta of the particle to reach the horizon should be in this range. And as we see from these plots, the increasing of parameter will also increase the range of possible values of the angular momenta. It's become wider. And so again, let us try to calculate the center of mass collision, and we again have not very representative form, but we have here, if the collision occurs near horizon, will it go to infinity or not? So let us see in two subcases when the rotation of the black string is maximal, and when the rotation is in general form, not extremely rotating black string. So for the extremely rotating black string, we get this formula, and we see if the angular momentum of the particle has some value equal to this, so we will have some infinite. So again, we see that for different values of the string parameter, we see the unlimited energy of the collision, while for another values of the angular momentum, the divergence region is located outside the horizon, and so this case is not interesting, but this case give us the infinite energy. So now let us look what will happen in the non-extremely rotating black string case. So in the energy in the center of mass independence on the rotating parameter show us that the unlimited energy occurs only when only for the case of the extremal rotation of the black string, and for another cases it is finite and not very big, not very large. But one can take into account such multiple scattering effects, and for example, it will start from the beginning. For the particle which for the particle starting its motion from the rest at infinity to get the black string horizon, its angular momentum should be in this range. But for example, particle can start its motion from this red point and can fall onto the black string, but its angular momentum is larger than is not lying in this region. So it is possible to, and this allowed regions are shaded, and that's why let us consider some particle which starts from infinity but with small angular momenta and gets reach the horizon of the black string, and they interact with some another particles, or simply it can decay to lighter particles and get increased angular momenta, LH minus delta. And if we will calculate the center of mass energy collision of this particle with some another particle, we will get this formula for the center of mass energy, and we see that it depends inversely on the square root of delta. And if it's this delta, which is the difference, which is small getting angular momenta due to the multiple interaction or decay, if delta tends to 0, so it means that center of mass energy can be infinitely large. And we can see that for rapidly rotating black strings, not extremal, and some values of string parameters, the difference is very small. So they're getting small additional angular momenta due to the collision in the near horizon region seems much probable. So in the conclusion, I just talk again about the main results. So black string can act as a particle accelerator, which means that the mechanism of the energy collision, which was originally studied in S2 topology, can be transported to S2 S1 or S2 R1 topology. And we considered this for 3 different cases: for static black strings, black string immersed in magnetic field, and rotating black string. And we have shown that the appearance of new integral motion leads to increasing of the energy. And the collisional energy of particles can be ultra high, not only for the extremely rotating black strings, but also for the black strings which is rotate not extremely, if we will take into account the multiple scatterings or decays of the particles. And thanks.